everybody, and welcome to this somewhat spontaneous webcast that I just decided to do very recently. And it's on a very unique topic that you don't hear a lot about. It's OSPF's Dijkstra algorithm. And the reason I'm doing this today is next week, in fact, I think it's like my 10th year of doing this, the day after Thanksgiving. In the United States, we refer to that as Black Friday. I always go live and do this big marathon webcast for people that want to join live. And we're doing one on OSPF. It's going to be a super deep dive into OSPF coming up, not tomorrow, but the following Friday, November the 26th. And I wanted to make sure you were aware of that so that you could get registered. But the goal of that, by the way, and here's the link if you want to get registered, just go to kwtrain.com/OSPF. And that's going to be at 2 p.m. Eastern Time on Friday, November the 26th. But the reason I'm doing this today is there was one topic that didn't really fit neatly into that deep dive. The reason is the deep dive is designed to get you ready for all of the OSPF topics on Cisco's CCNA exam blueprint, Encore exam blueprint, and a NARCE exam blueprint. We're going to be covering a lot of material. It may go 3, 4, who knows, maybe 5 hours next Friday. We're going to go deep, deep, deep into OSPF. But for whatever reason, Dijkstra's algorithm is not on any of those blueprints. So I thought, I really want my students to know about that as well. So I thought, you know what? I'm going to go live. I'll do maybe a 20-minute webcast, and we'll break it down. We'll go through the math of Dijkstra's algorithm. And if you just saw this pop up on YouTube or LinkedIn or Facebook and you're thinking, who is this guy and why is he so excited about an algorithm? Here's my super quick bio and then we'll jump into it. For those of you that don't know me, my name's Kevin Wallace and I've been doing this for quite a while. I've got a couple of Cisco CCAs in collaboration in enterprise infrastructure. I've been a CCA for over 20 years now, which is really cool, by the way, because after 20 years, you get to go into what they call lifetime emeritus. So I don't have to pass any more tests or pay any more money to stay a CCA for the rest of my life. So that's kind of cool. But I've been working with Cisco gear since 1989. I've taught courses for Cisco Learning Partners for about 14 years. And been doing this with my own training company for about 7 years. I used to be a network designer down at Walt Disney World in Florida, and I designed the network that ties together the Magic Kingdom and Epcot and the studios and Animal Kingdom. And I've written a bunch of books for Cisco Press, done a lot of videos for those folks as well. I was a speaker at Cisco Live a couple of times, got the Distinguished Speaker Award. Bottom line is, I love this stuff. I am passionate about these technologies, and I want to share one specific technology with you today. I got nothing to sell. We just want to talk about Dijkstra's algorithm. And I've got some terms for you to know before we jump into how all of the math works. And by the way, if you're asking questions right now, I'm not seeing those. We'll take a look at your questions at the end of the session today because I don't have anybody moderating the session for me. I've got it on another screen over here. So we'll jump in to those questions at the end of today's discussion, which again, I think will run probably 20 minutes or less. But some terms to know. First of all, what is Dijkstra's algorithm? Well, this is an algorithm. It's called the Dijkstra shortest path algorithm. And it's going to look at a topology, a map, if you will, and it's going to answer the question from any perspective, from any one point on that map, what is my most efficient, what is my quote-unquote shortest path to get from where I am to where I want to go? Now, we see this in your car's navigation system, or if you have, like on your smart device, if you've got the Waze app or Apple Maps or Google Maps, they're all using this Dijkstra algorithm just like the OSPF routing protocol does. And the way it's going to do this is by identifying all the different possible destinations. So here's another term for you. It's called a node or a vertex. And here in this sample topology that we're going to walk through mathematically in a moment, I've got 5 nodes, 5 vertices, if you will. And we're going to go from the perspective of node A and say, what's the most efficient way for me to get to B or C or D or E? And I'm going to build this most efficient topology in a table, and we'll be able to draw this little tree out. That's what's going on in the background in your navigation system in your car. And when you're navigating in your car, if there are 2 ways to get to a destination city, maybe one way is on this super highway. It's like the Autobahn or it's some interstate with a bunch of lanes. That might be a very efficient way of getting there. but if it's on sort of a back road with gravel on it, maybe not so efficient. So you would be given a different weight. When Waze or Google Maps, when they're doing their calculation, they assign a weight to the roadway. So if it's a big interstate, it might have a very low weight. And if it's a back road with lots of traffic lights and gravel roads and maybe cows crossing the road, maybe it's a much higher weight because you're not going to get there as fast going through that back road. However, on an interstate, typically it's going to be the same weight between whatever direction. For example, I live in Kentucky, and one of the big cities in Kentucky is Louisville. And if I want to go to Louisville, well, the cost to get to Louisville is probably about the same as the cost to get from Louisville back to me. Now, that's not necessarily the case in all topologies. Dijkstra's algorithm actually assigns a weight on a directional basis. Here's what I mean. Take a look at nodes A and B on screen. Notice that in this case, as is typically the case, there's a weight of 20 or a cost of 20 to get from node A to node B. What's the cost to get in the other direction from B to A? Well, that's also 20. That's normally going to be the case. In fact, with OSPF, that's almost always going to be the case. The cost going one way is the same as the cost coming the other way because the cost is determined based on the link speed. However, on a roadway, maybe one side of the road, the northbound lane possibly, is having some construction done. Some lanes are closed on the northbound interstate, but it's wide open southbound. In a case like that, an adaptive mapping program like Waze would be able to detect that. And it would give a higher weight, a less attractive weight, to the northbound direction that has all those lanes blocked. But again, with OSPF, it's probably going to be the same in both directions. So we say that it's a directed and weighted graph. So the nodes, that's A, B, C, D, and E. The lines between the nodes, the ones that have the weights assigned, here's the other term I want you to put in your notes, that's called an edge. An edge is an interconnection between a couple of nodes. Now, I'm going to go through two examples in this webcast today. I'm going to begin with the one we just looked at, which is just sort of a generic approach to Dijkstra. We're looking at these generic nodes. These might be cities. Who knows? We've got these 5 nodes, and from the perspective of node A, we're going to mathematically determine the most efficient path, the shortest path based on cost, to get to any of these other nodes. Then I'll give you a network topology, and I want to show you how to apply this to a network topology with a bunch of routers. So to begin with, we've got this table, and we're saying that we are on node A. And I want to find the shortest path to node B, C, D, and E. And what does that look like? What does my map look like that I'm constructing when I'm running this algorithm? Well, let's begin by saying we're going to start out on our node A is going to be our initial node. We're taking a look from the perspective of node A. Now, to begin with, I don't have any values in my table that says here's the path or here's the cost to these different nodes. So initially, I assume the cost is infinity. It's an infinite cost to B, C, D, and E. That's going to change, but that's just an initial assumption. So in other words, if I don't immediately have information about how to get to node E, which I don't, from the perspective of node A, I'm going to consider that to be infinitely far from me. So let's go to node A. From the perspective of node A, do I have a way to get to node B? Yeah, there's a direct connection from A to B. And what is my cost to get to node B? It's 20. You see that link, that arrow, that edge between A and B? It's a cost of 20. So I'm going to say in my table 20-A. Here's what I mean by that. It's a cost of 20 to get from A to B, and I'm going to get there via myself, via node A. So node A is for myself. I'm going to go directly, in other words, to B. Now, later on, to get to node E, perhaps, I'm going to get there via node C. But right now, I can get from A to B. It's a cost of 20. Can I get to C? I sure can. That's a cost of 20. And again, it's going to be, a cost of 10, and that's going to be via myself, via node A. Now that's where we have an issue. From our table right now, can I, sitting at node A, see node D or E? No, they're not connected to me. So until I learn otherwise, I'm going to consider nodes D and E to be infinitely far from me. So I'll put an infinity for both of those. Now, here's the step. Here's the big mathematical step we take as we're working through this table. From the perspective of ourselves, which is going to be our router when we get into OSPF, I'm saying how far is it to this network or this network or this network? In this case, I'm saying how far is it to this node and this node and this node and this node? I want to pick the lowest cost of any of those. I've got a 20, I got a 10, I got a couple of infinities. What is the lowest cost? C, isn't it? Yeah, it's got a cost of 10. So I'm going to highlight C, and by that I'm saying I have already found the shortest path to C. Think about that. Do you agree with that statement? Do you think this is the shortest path to C? I think it is, because I cannot get to anywhere in a cost of 10. So I could not go anywhere else and then suddenly come back to C and have a cost less than 10. Because currently I cannot get to any of these different locations. So C, that is our best path. The best path to C is directly from A to C. It's a cost of 10. So now as we continue to build out this table, we're going to say, oh, let's move down to node C, and let's take a look at the perspective from node C. And we're going to go through a similar set of questions. I'm going to say, do I know how to get to D? Yes. And now, careful with the math here. C is connected to D. And I wrote that it's 30C. And you might look and say, whoa, hold on, Kevin. Isn't it just 20 to go from C to D? Yes, but this table is from the perspective of node A. How far is it to get from node A to node D? It's going to cost me 10 to get down to node C, and it's going to cost me an additional 20 to get up to node D. So that's a grand total of 30, isn't it? So if I want to get from node A, if I want to get to the node of D, it's going to cost me 30, and I'm going to get there via node C. So I'm going to go to node C, and they'll get me there. What about node E? Yeah, C is connected to E. It takes 50 to get from C to E, but we're looking at this from the perspective of node A. So it's 10 to get from A to C, an additional 50 to get from C to E. That's 60 as a total. Now, what about the other two, B and C? I'm not connected to node B. C, we've already found the most efficient path. It's highlighted. So I'll just bring those numbers down. Again, the reason I brought B down is because C cannot see node B from where it is. And we've already optimized the route to node C, so I'll just bring that down. Now let's look at our remaining nodes, not including node C. We're already good on node C. Let's look at our remaining nodes of B and D and E and say, who's the lowest cost? Is it 20 or 30 or 60? Yeah, I think it's going to be 20, isn't it? It's going to be node B. So now we'll say that we have found the optimal path from node A to node B, and it's a cost of 20. So we're going to shift our focus over to node B and say, what's its cost to get to these different networks? And what's going to be the total cost from node A? Or to these different nodes, I should say. Well, let's begin by saying, yeah, B is directly connected to E. Excuse me, it's directly connected to node D. And it's going to be, let's see, it's 20 to get to B. It's going to be 30 to get to D. And then we've got so that's a total, let me think about that one for a second. Yeah, I can get to D with a cost of 30, but it's going to take 20 to get to me. So the total cost from A is 20 plus 30, that's 50. That's not as good as the route via C, is it? If I went via C to get to D, it was only a cost of 30. If I go from B to get to D, that's a cost of 50. I need to put the lowest cost in there. So I'm just going to bring down that cost of 30 to get to D via node C. Now, I can get to node, no, I cannot get to node E directly from node B. So I'll just take the previous value, cost of 60, bring it down. We now have two nodes that we've not already optimized, D and E. Who has the lowest cost? D. It's got a cost of 30. So now let's shift our focus up to node D. And on node D, we're going to say that, yeah, we've already optimized B, we've already optimized C, we've already optimized D. The only thing is left is E. Can D get to E? Yeah, it sure can. It's a cost of 40 what does it cost to get to D? Well, we said that the shortest cost to get to D is a 30. We go from A to C to D. That's a cost of 30. Then it's going to cost an additional 40 to get down to E. So that's a total of 70. Well, that's greater than the cost compared to what it would be if we have just gone from C to E. Remember, that was a cost of 60. So we already had the optimal path to node E and just didn't know it. So now I'll just bring all these values down. We've now optimized our path from node A to all of the other nodes. And if I were to draw this out, it would look something like this. I would say, here are my nodes, and I can get from A to B, and the cost is going to be 20. I'm reading that bottom row in the graph. I can get from A to B, the cost is 20. If I want to get to node C, I'm going to get there via myself, and the cost is 30. If I want to get to node D, where do I go next? My next stop is C. I'm going to get there via node C, and the total cost is going to be 30. If I want to go to node E, then I'm going to get there via node C, and the total cost is going to be 30. Or excuse me, the total cost is going to be 60. So this is our shortest path tree. This is what OSPF is going to be doing in the background with our networks. Instead of sitting at node A, we're going to be sitting on a router, and the router is going to be running this Dijkstra algorithm in the background. So let's take the basics that we've learned now, and let's do one more example, this time using a network. Now, before I do that, for those of you that joined a little bit late, one of the reasons I'm doing this training today is a supplement training to a super, super deep dive into OSPF that I'm doing a week from tomorrow. It's totally free. I do it every year on Black Friday. I think I've done it for about 10 years now. Just go to KW. In fact, let me see if I can put that up here. I'll put the link on screen. Just go to kwtrain.com/OSPF to get registered, totally free. And you'll want to attend live. I'm doing some special things for the live attendees. I'll probably leave a replay up for a few days after that, but you're going to miss out on some stuff if you don't attend live. So please make plans to join me live for that. It's at 2 p.m. Eastern Standard Time, November 26th. All right. Here's what the topics are. I said we're going to do a deep dive into OSPF. How's this for a deep dive? Everything from the basic OSPF theory all the way through how to do authentication, how to set up address families with OSPF version 3. I'm going to be doing a ton of configuration demos in this, and I'm going to try to simplify this for you because, personal confession, for the longest time, like I said, I've been doing Cisco stuff for 32 years now. I was really intimidated of OSPF for many of those years. It just seemed so mysterious. I heard about these LSAs, and you've got all these different LSA types like 1 and 7 and 5. What's up with all this? Well, I'm going to try to do the impossible on Friday, a week from tomorrow. I'm going to try to demystify LSAs. We'll talk about all the different LSAs, or the main LSA types, and I'll try to demystify those and kind of tell you a story along the way, along with demystifying all these other OSPF concepts. But back to our story. And I'll just leave that link for the OSPF registration on screen. But what we want to do now is take, using OSPF, a topology, a network topology, and figure out from the perspective of R1, what is my shortest route to get, or shortest path to get to any of these networks. Now notice something on screen. I've got router R1 showing up. It's sort of in the upper left, and it's not grayed out. It's not transparent. But you'll notice all the other routers, R2, R3, R4, R5, R6, they're kind of ghosted out. They're grayed out a little bit. You can see through them. The reason I made them a little bit transparent was to make a very important point here. When I'm sitting on R1 and I'm saying, give me the shortest path to this network, I'm trying to get to a network. I'm not trying to get to another router. So my OSPF table inside of router R1 is not telling me the shortest path to get to router R5. It's telling me the shortest path to get to router, or to the network 10.5.5.0/24 as an example. So the nodes here are R1. That's where we are. We're sitting on R1, but the nodes are not the other routers. The nodes are the other networks, 10.1.1.0, 10.2.2.0, and so on. So we're going to start our journey from the perspective of router R1. And we'll talk a lot about how cost is configured on a week from Friday when we get into this. We'll talk about how things don't work very well by default on a lot of Cisco routers, and we'll have to adjust what's called the reference bandwidth. But let's assume that I've adjusted the reference bandwidth, and a cost of 10 represents a gig link, and a cost of 1 represents a 10 gig link. Now, that's not the default. We don't like the default. But let's say I've adjusted the reference bandwidth, and we'll talk about that next Friday, a week from tomorrow, how to do that. But gig links are cost of 10 gig links cost of 1. I'm sitting on R1, and I'm saying, can I get to 10.1.1.0/24? Yeah, I'm directly connected. And I've got to go out of a 10 gig link to get there. So I'm going to say, yeah, I can get there via myself. Via R1, I'm directly connected to 10.1.1.0, and it's a cost of 1. Okay. Can I get to network 10.2.2.0? Absolutely. I'm connected to it out of my other interface. That's my gig interface. So I can get there via me, via R1, and it's a cost of 10. Now, at this point, R1 cannot directly see, because I cannot see through nodes. That's the key here. I cannot see through a node to see what network lies on the other side of that node. I'm saying, do I have other information about how to get to this network, or can I personally see it because I'm attached to it? Right now, we haven't taken a look from the perspective of any other networks. So right now, I'm not connected to 10.3.3.3, or excuse me, 10.3.3.0, or 10.4.4.0, or 10.5.5.0. So I'm going to say, right now, remember the initial assumption, the distance, the cost is infinity. All right, remember what we did in our previous example? What we did was we took a look at the costs, and we said, what's the lowest cost? And whoever had the lowest cost, then ding, 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 we have found the optimized path to get to that network. Well, the lowest cost here, between 1 and 10 and a bunch of infinities, it's 1. So 10.1.1.0/24, we have now found the optimal path, and it's via me. It's via R1. I'm directly connected. So we found the shortest path to that network. Awesome. Let's now shift our focus to that network. Remember, we're no longer sitting on a router, building a routing table. I'm saying from the perspective of this network, do I know how to get to these other networks? So now I'm on that upper left-hand corner network, 10.1.1.0, and I'm saying, can I get to these other networks? Well, I've already found the optimized path to 10.1.1.0 via R1, so I just bring that value down. What about 10.2.2.0? Well, I cannot see that from where I am now. I'm on 10.1.1.0. I'm not directly connected to 10.2.2.0. However, we already have information in the table about that network, so we'll just bring that information down. And that's going to be a cost of 10 via R1. Again, it's a cost starting at R1. All these costs that we're doing are starting at R1 because we're building the OSPF routing table for R1. Can my network of 10.1.1.0 get to 10.3.3.0? Yes, it can. You might say, oh, there's a router in the middle. That's okay. Remember, a router is not a node. Something interesting, though, is there is a cost to get to the router, and there's a cost to get from the router out to the 10.3.3.0 network. Because we're going in an interface with a cost of 1, and we're going out of an interface with a cost of 1. So what is my total cost? Well, remember, this is from the perspective of R1, so let's count it up. From R1, it's going to cost me 1 to get over to 10.1.1.0. It's going to cost me another 1 to get down to R2. It's going to cost me another 1 to get down to 10.3.3.0. So 1 plus 1 plus 1, yeah, it's 3. And it's going to be via this network, 10.1.1.0. Now, I don't have any way of seeing still 10.4.4.0 or 10.5.5.0, so I'll just bring those infinity values down. All right, excluding 10.1.1.0, which I've already optimized, who now has this lowest cost? Is it 10 or is it 3? Yeah, it's going to be 3, isn't it? And that's going to be 10.3.3.0. We've now found the optimized path to get from R1 to 10.3.3.0. So now as we're building out our table, let's shift our focus over to that perspective. We're going to step into the map here. We're going to go to 10.3.3.0 and we say, well, we already know that there's no better way to get to 10.1.1.0 or 10.3.3.0. We've already optimized those. But what about 10.2.2.0? Can I get there from 10.3.3.0? No, but we've already got a value in the table, and I'll just bring that value down. Can I get to 10.4.4.0? Oh, yes, I can. Look at this. I can get there. I could go up to R4 and then from R4 to that network, or I could go from R5. No, I could not. There's a network in my way. So the only way I could get there is to go from R1 to R2, R4, and then up to 10.4.4.0. What's the cost? What's the cost of 1 as we leave R1 going into that network of 10.1.1.0? It's another cost of 1 as we enter R2. It's another cost of 1 as we exit R2. It's another cost of 1 as we exit 10.3.3.0. It's another cost of 1 as we exit R4. And it's cost of 10 to get into 10.4.4.0. So if we add all that up, it's 3 plus 1 plus 14. I got a cost of 14 to get there. We're getting some high costs now, aren't we? All right, can I get to 10.5.5.0? Yeah, R5's transparent. I can see right through it. And it's going to cost me, again, 1 plus 1 plus 1 just to get from R1 to me. And then it's going to cost me another cost of 1 to get to R5 and another cost of 1 to get to 10.5.5.0. So that's 3 plus 1 plus 1, 5. That's total cost of 5. So from the perspective of R1, it costs me 5 to get to 10.5.5.0, and I'm going to get there via 10.3.3.0. So of the remaining networks that we haven't already optimized, who has the lowest value? Is it 10? Is it 14? Or is it 5? Yeah, 5's the least one. And that's for network 10.5.5.0. We've now optimized the path to that network. So we're going to look from the perspective of 10.5.5.0 and say, well, first of all, we already know the optimal path to get to 10.1.1.0, 10.3.3.0, and 10.5.5.0. But let's now say, can I get to 10.2.2.0 from 10.5.5.0? No, not directly. So I'll just bring the previous value down. Can I get to 10.4.4.0? Yes, I can. It's going to cost me one. Well, first of all, how much cost does it take just to get to me? Just to get to 10.5.5.0? We already said that's a cost of 5. All right. I've got a cost of 5. It's going to cost me 1 to get up to R6. So I'm now up to 6. And then it's going to cost me another 10 to get into 10.4.4.0. That's 16. That's not as good as what we already had. 14 is better than 16. So I'll just keep the previous value. What's the lowest value between 10 and 14? 10. So we've now optimized the route to 10.2.2.0, and we're going to shift our perspective there and say, all right, I figured out all 4 networks except 1. There just might be a better path to 10.4.4.0. Let's check it out. So I'm on 10.2.2.0. Is there a direct path to 10.4.4.0? There sure is. I can go over to R3 and I can get to 10.4.4.0. But from the perspective of R1, what's going to be the total cost? From R1, it's going to cost me 10 to get to 10.2.2.0. It's going to cost me another 10 to get to R2. It's going to cost me another 10 to get over to 10.4.4.0. That's a cost of 30. That's way worse than what I already had, which is a cost of 14. So now we've reached our steady state. We have now come up with an optimized path to all of our different destinations. So if we were to draw this out, we're starting from the perspective of R1, and it's going to cost us 1 to go down to 10.1.1.0. We're attached to it with a 10 gig link. It's going to cost me 1 to go to 10.2.2.0. I'm attached to that with a 1 gig link. But then to go to 10.3.3.0, that's going to be via 10.1.1.0, and it's going to be a total cost of 3 to get there from R1. I can then get to 10.4.4.0. Again, I get there via 10.3.3.0, and the total cost from the perspective of R1 is 14. and I can get to 10.5.5.0 again through 10.3.3.0, and the total cost from the perspective of R1 is going to be a 5. So that is my shortest path tree that OSPF has constructed using the Dijkstra algorithm. Now, because this algorithm is key to understanding how OSPF is doing things in the background, but it's not on any of the exam blueprints like CCNA or Encore or NARCI, I wanted to have a special little webcast today to cover this as we get ready for our big deep dive. Because so many people think that we've got a router, it receives all these link state advertisements, all these different LSAs, and a small miracle happens, and it constructs this table. I don't want you to think of this as a small miracle happening. It is a very predictable mathematical procedure, and we just went through it twice. So I hope you found that valuable. And we'll go ahead and take some questions for just a few moments. So if you've got questions, please go ahead and chat those in. But one of the main things I don't want you to miss is a week from tomorrow, we are going to have an OSPF deep dive. I don't know how long it's going to last. It's going to go maybe, I'd say at least 3 hours, maybe up to 5 hours. So clear your calendar. We'll do some special stuff for people that attend live. Just go to kwtrain.com/OSPF to register. And let's see if we get any questions here. Let's see. Kevin is saying, can cost be adjusted if a link goes down? Oh, that's a great point. Yeah, just like on the interstate, if we lose a roadway, for example, if somebody if somebody notifies Waze that this road is now closed, yeah, it has an increased cost if it goes down. Or basically the cost is infinity if an actual network link goes down, and we'll reroute around that. That's one of the great things about OSPF. It can converge, meaning it can reroute around a fail link in about 2 or 3 seconds. That's blazing fast. Let's see, what else do we have? All right, so, yep, see you next Friday. Let's see, we're on a few different platforms here. Let me check out some of the other platforms. What kind of questions are being asked? Let me refresh Facebook. I don't see any recent questions. Sometimes I have to refresh it to see the current questions. A few different platforms here. Let me refresh it to see the current questions. Nope. We were refreshed. We just didn't have any questions there. Not seeing any LinkedIn questions. Can I watch this podcast offline? It's going to be posted on YouTube. So if you have their premium service, I think they let you download from there. But I'm only going to have this up for like a week because I'm pushing, or I'm promoting that OSPF deep dive. I want to help as many people as I can on Friday the 26th. And it really wouldn't make sense to have this video up past then, since I keep talking about that link and it wouldn't work after that. So I'll keep this up for about a week on my YouTube channel if you want to go back and watch it again, but not a direct way to download it. Somebody says they tried to register but getting an error. There have been hundreds of people that are registered, so it could be a security issue. If you're behind a firewall, I would try maybe through your mobile device, through your cell provider. Try it home as an option. If you're leaving everything alone, then speed is what gives you the cost. Tracy is asking. Yes. And we're going to talk about this on our deep dive. It's really bad. Okay, I'm going past 20 minutes a little bit, but I do want to explain this. In case you missed next Friday, this is a key concept because so many people have a false sense of assurance about OSPF. OSPF says the way to determine the cost of a link or an edge from the perspective of a Dijkstra algorithm, the cost is the reference bandwidth divided by the link speed. So for example, if I had a 10 megabit per second, really old regular Ethernet, a 10 meg Ethernet connection, what would be the cost? Well, by default, now this isn't necessarily true for all the new Cisco Nexus equipment you might find in a data center, but for your traditional Cisco iOS routers, the default is a reference bandwidth of 100 meg. Okay? My reference bandwidth is 100 meg, my link speed is 10 meg, so the cost would be 10, right? 100 divided by 10 is 10. What would be the cost of fast Ethernet? What would be the cost of a 100 meg link? Well, it's my reference bandwidth of 100 meg divided by my link speed of 100 meg. 100 divided by 100, obviously that's just 1. Here's where we run into a problem. What will be the cost, by default, what would be the cost of a gig link? It would be 100 meg divided by 1000 meg. What is that? That's 0.1. A cost cannot be a decimal value. It has to be an integer. So even though it's 0.1, you've got to round it up to a 1. What if it were a 10 gig link? 100 divided by 10,000, that's 0.01. Again, got to have an integer, cannot have a decimal, so we round up to a 1. You see the problem? By default, OSPF gives the same cost to a fast Ethernet link running at 100 meg. It gives the same cost to that link as it does a gig link. It gives the same cost to that as it does a 10 gig link. That's horrible. Because so many administrators out there, they'll connect their network together and they just assume that, oh yeah, OSPF is going to make the best determination of the path based on cost. Maybe not, if it cannot tell the difference between those costs. So yeah, we'll want to set the reference bandwidth for sure. Let's see, we've got time for maybe one more question. Let's see. Each speed has a cost from the legacy. Yeah, we've talked about that one. Concentrate on the cost, not the speed. Well, I wouldn't really say, we had a couple of people saying something like speed is more, or cost is more important than speed. They're both equally important. You just have to make sure that the speed is calculating the correct cost, because by default, different speeds are calculating an overlapping cost. That's what you want to avoid. All right, I've already gone way over what I said I was going to try to do today. We've already gone about 35 minutes, so we will wrap it up. Again, I would love for you to come join me, totally free, like a 3 to 5 hour webcast, and my goal is to cover every topic on the CCNA, the Encore, and the UNARSI exams for the topic of OSPF. Lots of configuration. We'll be doing some special things for people with us live, so be sure and register and attend if you can. And whether you can join us or not, I want to thank you sincerely for taking some time out of your day and joining us for this brief webcast on the Dijkstra algorithm. Take care, everyone. Hope to see you next week.